This is shown. Okay, so your resistance, inductance, then shunt capacitance, conductance, all are uniformly distributed the entire section of the line. So now let us assume. So we have to do calculation. We will take some certain assumptions that the line has shunt admittance per unit length and a series impedance per unit length, and the characteristic impedance we noted as ZC. Any lossless transmission line is defined as the square root of Z by Y, where Z is nothing but R plus J omega L and Y is nothing but G plus J omega C. If you put the value of Z and Y, then the definition of ZE, that is characteristic impedance, is complex quantity. However, the transmission line lossless transmission line is R equal to 0 and is G equal to 0. Okay. So when we go to the lossless transmission line, that corresponding resistance and the conductance will be 0. Okay. So the remaining term Z equal to J omega L and Y is equal to J omega C to be present here. Now, if you take in the root, the characteristic impedance is C is nothing but square root of L by C. Then significance of surge impedance. Why surge impedance is important? So the significance of surge impedance is that if a pure resistance load that is equal to the surge impedance is connected to the end of the line with no resistance, voltage surge is induced by the shunt capacitor to the sending end of the line would completely absorbed by the series inductance at the receiving end of the transmission line. Okay, so this is very important. So we are having a transmission line. The transmission line is having inductance and capacitance. Okay, so the transmission line only have resistance parameter when we are applying the voltage. So after applying the voltage, there is a possibility of surge present in your system. So that surge from the sending end is completely absorbed by series inductance present in the receiving end of the transmission line. So whenever the voltage surge is presented, so that corresponding surge is absorbed by the receiving end inductance, inductive reactance or inductance. Okay, so that is very important. What happens if the line terminates in surging? Line terminates in surging. So if the transmission line losses terminates the surge impedance, that is, if the load is pure resistance of the value equal to the characteristic impedance of the line. Lossless transmission line, which is meaning is given by load is pure resistance of value equal to characteristic impedance of the line. So characteristic impedance of the line means Z not equal to root L by C. Okay, here the resistance is absent. Then the transmission line is known as infinite line or fixed line. So that in the case of many interesting phenomena happen in such lines. So there will not be any reflection of the forward traveling waves, and hence there will be no standing wave in the line. Therefore, the voltage will be same throughout the line. In the case receiving end and sending end voltage will be same. So when you are maintaining your transmission line as a lossless line, so that time you will not exhibit any voltage drop between from your sending end to receiving end. So that is the importance of your surge impedance. Then the line will be compensate itself, that is the reactive power demanded by series inductance of the line will be supplied by shunt capacitance. That's why there will be no voltage drop and also no voltage boost. So this is very important. The line will compensate itself. So the reactive power demanded by series inductance of the line will be supplied by shunt capacitance. That's all. So there will be no further problem will be arises to the system. So definitely we are using a more inductive load. So there is a shortage of your reactive power. So it is supplied by shunt capacitor. If suppose the line is not connected with the load, so there is an excess of reactive power. It is absorbed by shunt capacitor inductor. Okay. So it can build themselves. We cannot arrange any external sources to compensate each one. So this is very important. Then the load seen by the generator is purely resistance that will be equal to characteristic impedance. Hence the line is absorbed as equivalent to source of fire with zero resistance. So this is important. Then surge impedance loading. So surge impedance loading is nothing but it has depends on three factors. One is thermal limitation, I square R loss, voltage regulation, stability limitation. So in contrast to this limitation, surge impedance loading is an important parameter in electrical science to predict the maximum loading capacity of any transmission line. It is the maximum megawatt loading of the line and in which the reactive balance occurs. So this is very important. So how much maximum loading capacity of your line is calculated by only the surge impedance loading. So without knowing the proper data, we cannot able to send maximum power to the corresponding transmission system. So we need some pre-calculation is required to send the power for the corresponding line. So surge impedance loading is defined as the maximum load that can be delivered by the transmission line when the load terminates with the value equal to surge impedance of the line. Okay. So maximum load when we can able to supply the maximum load to the system is when the transmission line load when the loads are terminate with the value load is terminated with the value equal to the surge impedance of the line. Okay. So load value is at L, surge impedance is at S. So load value should be equivalent to surge impedance value, and we can send the maximum power. So this is related to your maximum power transfer theorem. Okay. Simply, if a line is terminates with the surge impedance, then the corresponding loading megawatt is known as surge impedance loading. If the line is terminate with the surge impedance, your end line terminate with the surge impedance. Surge impedance is square root of L by C. Okay. So square root of L by C, end of the line, we are having that much of impedance. So the corresponding loading megawatt is known as surge impedance loading. Surge impedance loading as the maximum load that can be delivered to the transmission line when the load terminates the value of equal to the surge impedance of the line. Okay. So this is very important. The maximum load that can be delivered by the transmission line when the load terminates with a value equal to surge impedance of the line. The load value should be equivalent to ZS. The load impedance should be equivalent to ZS. So this will create the possibility of sending very maximum power to the line. Okay. So in other words, we can define surge impedance loading. The maximum load connected to the transmission line for which the total reactive power generated is equal to the total reactive power consumed. So this is also another definition for surge impedance loading. So we are having the maximum load. Definitely in our system we are having the total reactive power generation and the total reactive power consumption. Okay. So we are having some kind of capacity war and some kind of inductive war presented. So this will be balanced. So at that time we can able to send the maximum load, maximum power to the system. Okay. So as to maintain an exact balance of reactive power compensation, consumption and the generation. So that's why by the set flow of reactive power in the transmission line will be zero, and hence transmission line is assumed to be loaded in a pre-existing load. So SI unit of surge impedance loading is megawatt. So this will be equivalent to kilowatt square divided by Z, kilovolt whole square. Then calculation of surge impedance. As we know, a long transmission line, more than 250 km long, as represented as a distributed parameter model. So in this model, the capacitor and inductors are distributed uniformly along the line. So when the line is charged, then the shunt capacitance generates the reactive power and feed into the line. When the series inductance absorbs the reactive power, and hence the voltage drop across the line due to series inductance and is compensated by the shunt capacitors of the line. So if we take a balance of reactive power due to inductance and capacitance, then we get an expression here. So the calculation of surge impedance is clearly indicated that we are having some loading of capacity load and some loading of inductive load. Whenever it is required, if we are having required of more reactive power, we are going to inject in the capacity load into the line. When we are having more reactive power in the transmission line, we are going to absorb the reactive power by switch on of your series inductive reactor. So that this is related to some calculation how much of capacity load and deck load will be earned for the corresponding time. So this will be indicated here. If you take balanced reactive power to the inductance and capacitance, then we get an expression V squared by X is equal to I squared Xc. So after solving this, V by I square root of L by C. So this is the surge impedance of the transmission line. Hence, the quantity having a dimension of resistance is surge impedance is denoted by the symbol ZS. It is considered as a purely resistive load when connected to the receiving end of the line. And then the reactive power generated by the shunt capacitance will be completely absorbed by the series inductance of the line. Okay, so this is regularly repeatedly told that. So what is the effect of surge impedance loading? If it is not properly maintained, so there is a problem. Okay. So from the above expression of surge impedance loading, we observed that the surge impedance loading depends upon the line voltages of the receiving end. Normally, the line is loaded above surge impedance loading for better utilization of the conductor. In other words, we can say that surge impedance should always be less than your maximum loading capacity of the line. So from the installation point of view, so we decided that that particular line will have the capacity of this maximum load. So we have to give the power to the line so lesser than that maximum capacity of the load. So when the line is loaded lesser than surge impedance loading, then it acts like a shunt capacitor, which means that it will supply MER to the system. So in this case, the receiving end voltage will be greater than the sending end voltage. In such cases, the line has to be compensated with the inductor to bring down the voltage to a normal value. So this is the problem. So when your surge impedance value line is loaded lesser than surge impedance value. Okay, surge impedance loading level. Then what will happen? Then it acts as a shunt capacitor. The corresponding thing will be act as shunt capacitor. Shunt capacitor supply your MER active power to the system. So then the end side, the capacitor charging current is added to the receiving end side, so that receiving end voltage will be more than your sending end voltage. Then there is a need of compensation. We have to balance our voltage so that we are activate our the shunt series inductor. So the series inductor absorbs the more MER in the system and comes into the system normal. Okay, so this is happened when you are going to apply the surge loaded lesser than surge impedance loading. Okay, suppose if your line is loaded above your SIL surge impedance loading, so what will happen that time? So however, when the line is loaded above surge impedance level, then it is act like a shunt reactor. Then it will absorb more MER from the system. In such a case, voltage drop occurs in the line. Due to this receiving end voltage will be very smaller than the sending end voltage. Then compensator is required to maintain the voltage level. So again, you have to do the compensation value. So in the transmission line, so we have to maintain the system as per surge impedance level. If it is lesser than, we are having a problem. If it is more than, also we are having the problem. So this picture will clearly indicate that the effect of surge impedance loading. So the below figure contains a graph of the effort of SIL surge impedance loading for a particular line of SIL value 450 megawatt. 450 megawatt here, 450 megawatt is here. So if the line is loaded to 450 megawatt, then MER produced by the line will exactly balance the MER absorbed by the line. Hence, there is no flow of reactive power in the line. So this is very important. Okay. So what is your maximum loading capacity? So that loading capacity equivalent to that C4 is produced by the line and observed by the line. So we have to ensure it. If it is not balancing, then there is a need of compensation. Then the compensation device is activated by themselves and solve the problem. So and also then surge impedance loading related to your voltage and the length. Okay, if the loading is equal to surge impedance, then voltage profile of the line is flat here. So voltage profile is very flat. Suppose surge impedance loading is greater than surge impedance, then line has inductive nature. Here. Suppose loading is lesser than SIL, line is capacitive nature. And how to improve surge impedance loading. If you are the problem, if you are not maintaining surge impedance loading, definitely we should go to the compensation. We suppose what is the remedial measure to improve your surge impedance loading. So from the above expression of surge impedance loading, we observed that transmitted electrical power through a transmission line can be either increased by increasing the value of the receiving end voltage or by reducing the value of surge impedance load. So the two things happen. So surge impedance load is nothing but kV square divided by ZS. So whether we can increasing the receiving end voltage or we can reduce your surge impedance loading. There is two possibility from the expression. Okay, right. Since the voltage transmission capability is increasing day by day, so the most commonly adopted method for increasing the power limited of the heavily loaded transmission line is increasing the voltage level. However, there is a limited behind which it is either economical nor practical to increasing the receiving voltage of the power network. So day by day the voltage is increasing, requirement is very high. So we cannot able to reduce the transmission line voltage for a certain problem. So this is not the logical thing. Okay. So we have to go with the alternate solution. So another option is by reducing the voltage of surge impedance ZS value or characteristic impedance of the line, so we can easily improve the surge impedance load. Okay, so one thing is uh, maintain your receiving end voltage. Other thing is maintain your surge impedance value. So these are the two possibilities to improve your surge impedance loading. So because it depends on only two factors. Right. Since the surge impedance is directly proportional to the inductance and inversely proportional to the capacitance, ZS is nothing but square root of L by C. So hence the value of surge impedance can be reduced either by increasing your capacitance or decreasing the inductance of the line. However, the inductance of the line cannot be reduced easily. So inductance of the line cannot be reduced easily because all maximum loads are inductive nature. Already it is a reduced value only. So that particular line needs the capacitance induction only because to compensate the reactive power. But very rare case it required the series inductor operation. So further, the capacitance value can be increased by the two ways, either by using the series capacitor or by shunt capacitor. There are two methods to improve the surge impedance loading of the transmission line. One is series capacitor, another one is shunt capacitor. By the use of series capacitor, surge impedance and the phase shift gets reduced due to decrease in inductance value. So it also improves the system stability. The capacitor also helps in reducing the line voltage drop. But the main problem with this method is causes difficulty under the short circuit condition as the series capacitor will get damaged. So this is the problem, regular problem. So when you go with a short period of operation, so this system will get failure for any fault is appearing in the system. Okay, and also using of shunt capacitor. So also use the shunt capacitor, surge impedance reduced by the phase shift of the system increases. This affects the poor stability of the system, especially when the synchronous machine are presented in the load. So this method is not feasible when stability limit to the main concern in the power system. So when we are talk about the stability, so this shunt capacitor method is not feasible one for to maintain the stability. Okay. So, so up to this presentation, overview of the presentation is first thing we discussed about the characteristic impedance of the line, two parallel line. So here there we discussed about Z is nothing but square root of LBC. The same characteristic impedance with the lossless system, it comes into the surge impedance. Okay, the surge impedance important is very important thing. So based on the inductance and capacitor early, we comes into the factor of surge impedance. Then after that surge impedance loading mainly deals with the maximum loading capacity of the line. So when we can able to send the maximum power to the line. Okay. So what about the required compensation? So is required for series capacitance or shunt capacitance or series inductor. So the operation is required only for the operation of your surge impedance termination of the line. So thank you for your question.